I'll go ahead and get started. My name is Truncer. This talk is it's titled Bringing Down the House, How One Python Script Ruled Over Antivirus. A little bit of quick background on myself. I am a sysadmin originally, or was a sysadmin, and then I turned into a red teamer / pen tester. I'm a red team lead at Mandiant. I live in Colorado, so a little ways from here. I'm also an open source developer. I work on Veil, Eyewitness, a couple other Python-based tools that I enjoy doing. So what this talk is about, I'm talking about kind of like the PenTesters problem, kind of what was the origination of this tool that I worked on called Veil. I'm going to go into shellcode injection, which is probably going to be the most technical part. I'll try to make it as easy as possible. It's a fairly easy concept. Then we'll talk about Veil-Evasion, Veil's approach. We'll talk about a AV signature bypass, and then I'll get into any questions if there are any. I do have a lot of slides in here, so I'm going to go kind of quick. I did tweet these out to PyCaribbean, so in case anyone wants to look at these slides because I go too fast, they're online right now, so you can review them as well. All right, so we'll kind of get into this PenTesters problem that we have. PenTesters, red teamers, our job is to test the security of something. So this may be a web application that we're going against. This may be a thick client or some sort of program that someone wrote. It could be an office's internal network. It really anything. The way that we do tests is they are objective-oriented by nature. So we're not here trying to go around and just like hack things just because it's really funny and cool to do so. No customer of ours would get any value out of that. So we're objective-oriented where the customer, maybe the thing that they care about is, can an attacker access our payroll system? Can they access this heavily guarded secret recipe that we have? If there's a customer list that we just don't want to get out anywhere, can a hacker access and obtain that data? So these are the types of things that we go for when we perform security assessments for companies. So you kind of think of this like sometimes this is our job. Like it's not as often, but we dress up. We try to find a way to get into a company to, by whatever means, to physically obtain access to something, whether it's a developer's workstation or a server room. More often than not, this is our actual job, where we are sending phishing emails in. All the stuff that people tell you don't click on links, that's because we're actually trying to do that. And this is the easiest way for us to get in, whether it be PayPal, whether it be banking, whether it be some other scenario that's really similar to your work and what you do. So the reason we do this is at some point when we try to hit our objective, whatever that may be, we need to compromise people's workstations. So like where they work. In addition to that, we also do servers. So one way that we do that is we have to introduce basically a computer virus. Now, the good thing is these are, we like to think, controlled viruses, where they come back to only systems that we specify on ports that we specify. So this isn't a worm where we're just releasing something and it's just eradicating like every system and resource in a company. So we need to introduce viruses that allow us to control machines remotely. The problem is we, as white hat hackers, run into the same problems that real attackers do. We've got McAfees, Symantec, Kaspersky, any of these other AV solutions out there that people sell to try to protect your endpoint system. So what our problem is we need to figure out how to bypass antivirus. And we discovered that, unfortunately, this is relatively trivial. And I'll do a demo of that in a little bit. What we wanted to do is, okay, we know that we can bypass antivirus. Sometimes it just takes time for us to do so. And so, I mean, this could be a couple hours, however long that it seems to take for us to create something for that specific computer we're trying to hack. And so we were trying to figure out, okay, let's just like come up with an automated tool or means to just do everything that we need to do. And it produces like a virus, essentially, that bypasses AV. And so we would rather have that happen, have a tool create this virus so that we can spend that time actually assessing our customer versus spending the time creating some antivirus bypassing malware that is time taken away from testing the security of our customer. So we did that, myself and 2 other individuals, and we created this tool called Veil-Evasion, which is a completely Python-based tool. We developed this framework. And so there we go. Myself, Will Schroeder, and another individual named Michael Wright decided to create this framework. What it does is when we first started, it aggregates all of these publicly available AV bypass techniques. And so a lot of people run into the same problem. It was really cool though, because we didn't have to like reinvent the wheel. We can go out there, just aggregate all of these different techniques into one tool, and we have a basis right there. Next, the part that we wanted to do was it also automates the customization and compilation process. So what I mean by that is you need to customize this virus saying, hey, connect back to this IP on this port, and you can do that really easily. It also automates, kind of like I said, compiling it. So if it's Python, Golang, whatever language it is that your malware is written in, it'll compile it for you. You don't have to go anywhere else. It just basically spits out a Windows executable. The final thing that we wanted to do was kind of modularize this tool to make it really easy to add in new techniques. So let's say we originally started off aggregating all these different public techniques, but you or myself or someone else develop like a new payload that you want to create. Well, rather than have to go through all these different things, we made the tool where you just drop it basically into a folder corresponding to the language you wrote it in, and the framework will auto pick it up and auto handle all the compilation. If it is a compiled language, it'll handle compiling it and just spits back out the executable for you so you can use everything right away. The output of Veil is what we call a stager. It's a Windows executable that is a stager. And all right, real quickly now, we'll talk about like what a stager is so you can kind of grasp this. Stagers can be referred to as stage 1. So just picture like a really tiny Windows program that the only thing that it does, its main goal, is to inject what we call shellcode into memory. Now, I'll show what this is in just a second so you can visualize it. But basically, it's code that injects additional code into memory and runs it. Well, the purpose of shellcode is to usually connect to a remote system that you as the attacker would control, and it receives additional code. And so this is your real malware. So a good way to think of stagers, these tiny executables that Veil makes, is it is a loader for your real malware. So you would go, it runs, receives the real malware all in memory, and then gets that up and running on the system you're trying to compromise, and then you're good. And so the reason for that is that you don't actually send the customer your real malware and put it on disk, because that's a chance for antivirus to actually scan it. When you do this all in memory, which is how stagers work, AV generally doesn't actually, can't scan memory, and so it just doesn't see anything. One thing that we discovered was any language that has access to Windows API can be used to write stagers. And so this is really cool because the first language that I really learned was Python. And I was like, okay, hey, Python has this awesome library called C-types. We can use that to interact with the Windows API. As a result, you can write a stager in Python that loads malware and see how it works on a computer system. Like, is that caught by antivirus or not? And so there are two individuals that both developed proof of concepts for how to do this in Python. And these are the function calls. I'll kind of just real quickly describe them. It's a good way to think about it. It's just only 4 function calls you need to make. The first one is you allocate memory. The second one copies your shellcode into that memory that you allocated. The third function call actually then creates a thread, and it says, hey, run that shellcode in that memory that I allocated. And the fourth function call, all that does is say, hey, let that thread just run. Don't exit the program. Once that thread is complete, then you can actually exit the parent program that's calling it. And so it's these specific functions, which is virtual alloc, RTL Move Memory, create thread, wait for single object. This is the most C part of the talk, so I apologize. But this is kind of what it looks like. So this is actually a C based stager. And so this is shellcode. And so this is code where what this job is to connect back to an IP and a port and receive your real malware. That's all that this does. So I want to run this shellcode, and so I need to use those same 4 function calls I just talked about. And so right here, let me zoom in for you. Oops. Right here is that virtual alloc. It is the RTL Move Memory. So that create thread and wait for single object. And so that's those same exact 4 function calls I talked about. That's all you need to write a malicious stager, essentially. And so this is it in C. This is it in, oh, that's hard to see, I apologize. So this is Python 3. You'll see Python 2 version with the black background, where it's the same thing. We have this shellcode here. We're explicitly defining it as a byte structure. And then I'm calling virtual alloc, RTL Move Memory, create thread, and wait for single object. And I'm doing that with C types. This would be, so here's a little bit easier to see. This is in Python 2. Same difference. We have our shellcode here, virtual alloc, RTL Move Memory, create thread, wait for single object. So this tool, Veil, generates this source code. And I know it's hard to see. I'll show you in a second on a demo. But it also tries to obfuscate code as much as it can. So like we're importing C types as an alias right here. And for certain areas, and it could be obviously more done, this code kind of just looks like garbage because it's designed to be somewhat obfuscated where it's hard to read. And ideally hard to write an antivirus signature for. So, oh God, this is really hard to see. The way that the actual module works is we tell it, hey, I apologize. These slides are online, so you'll be able to see it. What I'm saying right here is, do you want to compile this code into an executable, and how do you want to inject your shellcode into memory? One of them is virtual alloc, what I was going about. So what happens, this is what the actual module in the Python framework looks like. These are required options, so you can say, hey, does the user want you, do you want the user to actually compile their Python code and create an executable? Or do you just want the source code to it? And so you can verify the source code and then compile into an executable any other way that you want through your own means, like py-to-installer or py-to-exe. This is also what these modules look like. So up above was that required options where we specify, is it allowed to compile or not? This is the actual module, what it looks like. And so this is where you're seeing, this is Python 2. We stored the shellcode in this byte array. We are importing C types with an alias. We're then calling like RTL Move Memory, virtual alloc, and all of these different spots here is just the variable names for that randomized code where we're trying to introduce as much randomness as possible to prevent a static signature from being created on just C types or something like that. And again, I'll kind of go into a little bit more of a demo to help make this make a little bit more sense soon. So our approach to beating AV, the way that we try to beat antivirus with Veil is we try to do it through a variety of different techniques. One is increasingly introducing more code obfuscation because we don't want it to be just virtual alloc, RTL Move Memory, create remote thread, wait for single object. If antivirus saw that every single time, then they could be like, okay, this is probably Veil output. This is probably malware. We should probably flag this. We use encrypted code where either the shell code or the function calls that we're calling are all encrypted. And so on disk, you can't see anything. And at runtime, it uses a key to actually decrypt that code and then execute it all. And the other thing that we do is obviously, because we're using Python, is we write these stagers in non-kind of standard languages for Windows binaries. Like when everyone thinks of a program for Windows, usually it's stuff written in like C#, C, C++. You don't generally think of like, hey, this program is written in Ruby or Perl or Python that we're running on my Windows system. So some of the different languages that Veil actually supports is Python is the #1 because we have the most modules there. Most of our guys, we have the most experience writing in Python. But we also support like Perl, PowerShell, C#, Go, Ruby, and so forth. So this is, I'll get into like why we started writing this with Python now, is kind of like what I had mentioned. We observed that when we write a payload that is not in C or C#, that actually made a really big difference. Antivirus does not really know how to inspect Windows executables that aren't in C or C#. It's like it just doesn't know how to find out the true nature. Is that really malicious, or is it benign and it's a good program to run? And so here's an example for C. And so we're kind of going back to, this is that original code that I showed originally. And this is the C version of a stager. And it has everything that we talked about, virtual alloc, those 4 functions are shellcode. And this is Python, Python 2. So this is, again, same thing. The thing to notice is this is literally the exact same program. This is the exact same shellcode, the exact same function calls here and here. It's just, obviously, we're importing a library, but we're calling the same exact thing. What we noticed was simply by changing the language that the executable was developed in, antivirus completely bypassed all antivirus engines. Everything that it saw, or every Python payload, it was just like, I don't really know how to look at this, so let's just say it's good. It didn't hit any like known bad signature. So at this point, I started really heavily investing in Python module development because we saw that it had no idea really how to look into this. And so this is through a couple different techniques. We're like, okay, let's do some basic letter substitution where every time the letter A is in our code, we remove that and replace it with Q. And at runtime, that letter is swapped back and then all the code is run. We do have base64 encoded shellcode or encrypted shellcode. There's a bunch of different ways. And so one of the cool things that we actually did was developed a payload which brute forces itself. And this is based off of another existing tool out there already called Hyperion. And I'll kind of go over this concept. So at runtime, this program has to brute force itself. So what it has is all this encrypted code inside of it that there is no key for. It only has part of the key. And the way that we're doing that is we're using a constrained key space. So let's say we're like AES encoding something. This is the first part of our encryption key. And this is 26 characters, I believe it is. So this can be completely random, and this is actually embedded inside of that Python code in the Windows executable. However, this last like 6 characters or 6 spots of the key, we don't know. That's not included inside of it. So if the code tried to decrypt itself just with this, it would fail. Well, what we do is we're using a constrained key space because I know all the time that these last 4, 6 characters are always actually going to be numbers. They're not letters, they're not symbols, they're only numbers. So then it makes it a lot easier for me to, okay, let's just like brute force and guess our way through the key space until we find it. And so that's exactly what we did, is the program, here's a better way of looking at it. The program has that known key, or the known part of the key, and then it loops over that actually should say 100,000 to 1 million. It'll start at 100,000, and so it'll say, okay, let's start with that known key, and then let's add the string 100,000 to that. Does that then inside, okay, does that actually decrypt the shellcode and decrypt everything? If it doesn't, no, let's go back to the beginning, and now let's reiterate to 100,001. Does that decrypt the shellcode and all the functions? No. Okay, let's go back to the beginning and go 100,002. Eventually, we're going to find the right decryption key. When that happens, it says, okay, hey, yeah, that works. Now let's decrypt all of our code and then inject that shellcode like I was showing earlier. And so we're able to really kind of easily just make obfuscated code hard to figure out what's going on, where even the program itself doesn't know its own encryption key. It has to figure out every time it runs.
Who are you protecting yourself from? A human inspector or?
Great question. This is really against antivirus programs itself. I don't expect anything like this to actually withstand a real malware analysis, and that's not what I'm trying to protect against. What Veil really is designed to combat and fight against is on-disk detection. So like whenever you save a file to a program or to your computer, AV will really quickly like scan it, see, okay, does it match any like known signatures? Does it do malicious stuff? That's what it's more going against, because we're trying to hide like its inner nature, and where they can't just like look at it, say, yeah, this is malicious, when everything that it's doing is actually encrypted and only run at runtime after it finds the key. So real malware analysts, they'll tear this apart. And so this is actually what that kind of code looks like. Again, this is like really not pretty, but I wanted to show you the real code. This is let me zoom in for it. Up here is the actual key. So this is that first part of that key that I was talking about. And then right here is where we're iterating over a range. And so this is the key as a whole. So we're saying, hey, take that key, that part of it, append the value of whatever I'm currently at in my loop, and then create this new AES object. And so the way that it's testing to figure out, okay, did I find the right key, is it'll attempt to decrypt this random string right here, which is literally just a string. It says, hey, does that decrypted value match this? If that does match this, then I know I have the right key, jump in, decrypt all my shell code, run the rest of my malicious stuff. If that doesn't match, then we're just going back up to the top and going over to the next value in that loop and creating a new key to see if it actually works. So this is kind of what that actual code looks like. All right, so now we'll get into this part about AV decided to write their own signature for Veil. After about 1 year, so this is 1 year that Veil kind of just was able to run rampant, AV decided that they were going to try to create a signature for it. And so this is actually, I believe, McAfee. I can't tell on here. And so I was like, okay, that's awesome. Like, this is a step in the right direction. This is what we wanted, that AV to like up their game, start looking at executables properly to then make better decisions if stuff is malicious or not. Previous attempts, though, by companies to like try to categorize Veil, okay, is this malicious or not, were kind of humorous. Here's an example. McAfee says that Veil, like its website, is a sports website, which is not at all what it is. So it was kind of funny, and we wanted to try to figure out, okay, what's going on. So this is the actual malicious code that was signatured. AV wrote a signature for this. So random question, there's no wrong answers. What would someone try to do? Like, what would you guys do if this was your code and you want to figure out if you could bypass it? What would you try to do to change something or do something to see if you can miss it? Go for it. Yeah? Yeah, you could, yeah, exactly. Like if you add like higher level stuff that just does nothing, absolutely, that's one way. Anyone else?
Like compute other random things. Like,
Absolutely.
take some of the code that just does some math and throw it in there somewhere.
Absolutely. Those are all valid ways. And the funny thing is you guys are thinking like a lot smarter than what I was when I was doing this. What I saw when I was looking here was like, hey, I see this word C-types all over my code. So I'm importing it up top, and I'm importing it all throughout the rest of this code. Like, what if something's here? Like, what if they're just kind of keying off of that? Like, so let's check. So this is the actual module for that piece of code. And so you can see right here, I'm importing C-types. Right here, I'm generating just like random values for the rest of the code. And then here's where my shell code is, and so forth. Here's the diff. You can't see, this is red up here. So this is red. I'm now just aliasing C-types. I'm saying, hey, let's alias that as AVLOL. And you'll see down here, I'm basically just doing a find and replace on the string C-types with the string AVLOL. And so this is now what that code looks like. We're just importing C-types as AVLOL. And it's all throughout the rest of the code. No more C-types anywhere. And so we're like, okay, let's do this. Let's see how it works. Funny enough, the second that we generate that code and we scan that with McAfee, completely bypass the signature. So literally just making one tiny change to the source code resulted in a complete AV bypass. And so this is what it looks like now. You're like, okay, well, what if AV LOL was in here? Well, now we're actually just generating like a random value of random length every time throughout the rest of the code and using it that way. So the other thing that goes along with this, and you'll see it in the demo, is we wanted to make Veil fairly usable, where wine became our best friend. So we're generating all these Windows executables in Linux. And so the way we're doing that is we actually have to install Wine on Linux, install Windows Python in Wine on Linux, and then install all the required libraries, so any like crypto libraries or anything like that. And it'll create a Windows executable. It's really a disaster to think about, that everything you have to do. We expanded that concept to go for all these different other languages, where now we can compile Windows programs in Linux, largely because we're using Wine in Linux, and we're tricking the interpreters to think we're actually in a Windows environment. This, yes, it takes up a ton of space, unfortunately. But the main reason is because we want it to be usable real easily, that someone can just run Linux and then actually get their Windows output. The reason for this, that we chose PyInstaller and Py.exe, is because we wanted AV companies that wouldn't just flag based on like the output. Some companies did this anyway, where like if we just do hello world, like go Veil, AV companies are thinking like it's just weird viruses because they just don't know how to properly inspect Python. So I'll give a quick demo of what this looks like, and we'll call it. All right, so I'm going to start Veil. I'm going to tell it to list. So I have Veil-Evasion, use 1. And so there's 43 different payloads that are in it. Oh, I'm sorry, no one can see this. So there's 43 different payloads that are in here. So if I want to list them, I have Ruby, Python, PowerShell, and so forth. So if I use this one, it'll just be flat, like no encryption, no obfuscation at all. So I'm going to say, let's use payload number 35. And so here are those required values that I was talking about earlier, where yes, like we wanted to compile into an executable. Everything here looks fine, so I'm just going to say generate. And here is where I specify, okay, what type of payload do I want? How do I want it to connect back to me? And what like IP import should this stuff connect to? So I'm going to say connect back to me over a TCP connection. I'm going to set my IP to my current IP. And I'm going to set my port to the port that I wanted to connect back on. At that point, it generates the shellcode. And then now I'm just going to say, hey, what's the name of the file I want to create? So let's say demo PyCaribbean. And I'm going to say, okay, let's use PyInstaller, because I can choose between PyInstaller or Py.exe. And so now this is running in Wine. It's generating this executable, and it'll output it. And so right here is that executable. So I'm going to copy that over to my Windows machine. And back up. And here I have Windows 10 running the latest version of Windows Defender. There's my file right there. We're going to scan it with Windows Defender. It says everything is clean, nothing is malicious, and I can run it. Nothing pops up, doesn't look like anything, it's just running in the background though. And right over here it's telling me, hey, I've got a session on my system. So I can do certain stuff. Oops, sessions 2. So I can do like ls, and here's the files, my desktop. I can find who my current user is. I can upload, download files. Like you can do anything with this tool. Basically. And so it's just, with Python, we're able to really easily bypass it. I've got one more slide, 2 more slides, excuse me, and I will be done. So that's a real quick demo. The main point of this whole thing is to showcase that static string-based analysis is dead. It doesn't work. It's easily bypassed. What we want is like AV companies to move to more dynamic-based analysis. We're actually looking at what the malware does, or reputation-based, which is what Symantec does, where they're like, hey, I've never seen this program before, and no one running Symantec has seen this program, so it might be malicious. So ending it with I think it'd be good. We want people, anyone, to be able to start testing the security of security products so you can know the level of protection that they provide. You can determine if there's a level of risk now introduced to your environment because of that. And Python is an easy way to do it. Like, we can do everything I just demoed was pure Python based. So you can test and know how well your security works with Python. And that's it. Any questions?
Question. Have you considered adding, let's say, for encryption parameters, for example, if I can pull something from the BIOS and an ID of the machine, a serial number, or something like that, and use that as part of the encryption. So my executable is only targeted, let's say I'm doing persistence, and I'm going to be using Veil to encrypt my persistence payload. And I want that payload to only run in the machine that I'm going to be persistent in. So if somebody takes that executable, brings it over, let's say, to a FireEye product or to any other company product to do static analysis on it, let's say Google Blocks or something like that, it won't execute it because it is not my machine.
That's a, yeah, that's an excellent idea. For Veil 2 right now, which is what is out, it doesn't have that in there. However, in 1 week, Veil 3 is being released. And I have some sandbox-based stuff where you can specify the minimum number of processors required to run in that system, the host name that it has to run on, the user account that it has to operate under, a couple other stuff like that, things like that, where if all of those checks have to hit, only if those hit will it then start running the primary code. If none of those hit, it just exit out normally like a non-malicious program ideally. I don't have, that's a really cool idea to do, like, based off of GUID or something like that. I don't have that in yet, but that's an excellent idea. That would be something to better that.
Probably you can do, let's say, a double crawl, or BIOS.
Yep.
Get one of those parameters that is unique to that box, and then that is going to be my key. So I remember at work when we were doing all the version engineering for Stuxnet, there were like 6, 7 modules. Mm-hmm. Some of them even 15 megs in size.
Oh, jeez. Yeah.
That we could never reverse engineer because what it was actually doing, it was pulling a bunch of parameters from the machine. But in the internal code, we didn't know how it was concatenating those to come up with a derived key.
Yeah.
So
that makes sense.
So we had a ton of modules that we could never analyze and work with because they were AES encrypted and we couldn't enforce them.
That's, yeah. That makes complete sense, and that's actually would be a lot more sophisticated than what I have in. It would be really cool, though. That's a great idea. Thank you. Anything else? Yeah.
You can add extra code to report the IP address of the running machine.
Can I what with the running machine?
Add extra code to the exploit to report the IP address and something else.
That would be the payload.
Yeah, I mean, the payload, we can do whatever we want. Right now, it just runs this basic stuff. But if you wanted that executable, that payload, to run extra code or do additional things, we can easily modify the template that it bases that stuff off of and then add that additional code and it would run. All right. Thank you, everyone. If anyone wants a Veil sticker, more than welcome to come up and have one. But thank you.